Greetings, Concrete Freaky Deeks. My name is Tyler Lay. And we've been talking about concrete, right? What are the ingredients again? Rock, sand, water, and cement? Are all cements the same? Well, we've been kind of treating them like they have been. But we're going to find out today that there's all kinds of different cements. They can do all kinds of different cool stuff to make your concrete perform in really cool ways. Let's get started. We can make concrete with all kinds of different types of cement. The most common cement, though, is Portland cement. Some people call Portland cement ordinary Portland cement. I don't really think it's that ordinary, right? I think it's pretty amazing. But they call it ordinary Portland cement because there's lots of other types of cements out there. There's lots of other things you can do with your cement. And this is short for this. There's an acronym called OPC, Ordinary Portland Cement, OPC. I like to think of this as kind of like if Portland cement was like an old school rap star. He'd be the OG, the original gangster. Get it? OG, OPC. Ha ha ha. Yeah. As you change the chemical composition of a cement, then you can change the performance. It's kind of like when we're making cement, as we've talked about before, if you change the chemistry of the materials that are going in or the amounts of different components coming in, you create a cement with different composition, different actually phases. And these phases can be responsible for different performances in the concrete. Now let's start out with really simple OPC. Just get started. OPC is traditionally characterized with ASTM C150. And they give you these different types. And these different types are based on composition primarily, which I'll talk about in just a second. But type 1, and these are all types that you're going to need to know so you can talk concrete with anybody. Type 1 is general use. Just general, everyday cement. General use. Type 2 is known as moderate sulfate resistance. And say, well, how do they do that? How do they give it moderate sulfate resistance? Well, they actually limit the C3A content, the tricalcium aluminate, and they limit it to be less than 8%. This is the monosulfate and the etronite, which we'll talk about coming up, are attacked by outside sulfates. I know, yikes. But if you limit them, then it's not that big of a deal. Type 3. This is high early strength. High early strength. And the way you get that is you grind it finer. You grind the cement to be finer. So this costs more energy. This is not as sustainable as other ones, but if you need high early strength gain, you can do it. You can do it. You can ask for a type 3 cement. Now, type 4 cements. Now, those are low heat applications. Low heat. Okay, and these are rare. They're not made that often anymore. But if you ever have like a mass element, like a really big element, like a concrete dam or a huge concrete column, and you want to make sure the concrete doesn't get too hot inside of it, low heat's a good way to go. But it's not used anymore. It's just not made because there's other ways to get low heat. There's other ways to get there, which we'll talk about coming up. You would use something like a fly ash or a slag, something that doesn't produce as much early age reaction. And there's type 5. And this is high sulfate resistance. And in this case, you're going to limit your C3A content to be less than 5%. So this is where you really are concerned about sulfate attack for your concrete. Sometimes, if things aren't super bad, you can get away with a type 2 and maybe a type 2 with some other additives. But if things get really bad, the only way to go is a type 5. Just really limit that C3A content as much as you possibly can. So just to recap what these things are for. Type 1 is general use. Use it for all kinds of different stuff. Type 2 is usually used when you have moderate sulfate. Some kind of sulfate in the soils, but it's not super high. Type 5, that's high sulfate. That's very special cases, but if you have to have type 5, then you got to specify it. How do you know? Well, you have to look at the soils and the water around the concrete and if the sulfate's high or not. Type 3, that's if you want high early strength gain. You want to get something early, open early or fast, or you want to do something like precast concrete, where you want to get your forms emptied and filled again as fast as humanly possible. That's where type 3 cement's really, really helpful, because you just need to get enough strength fast. And then type 4, what's it for? It's for large elements, produce lots of heat, okay? But it's not made anymore. Now, there is something else out there called white cement. White cement is Portland cement. Reacts a lot like Portland cement, very, very similar, very, 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 very similar chemistry, but there's very little iron and manganese. Okay, they very specifically find materials with very low amounts of iron and manganese. And the cement's not really white. It's actually kind of hydrates and it's kind of yellowish a little bit, okay? But it's a lot more white than Portland cement is, which is typically gray. But it's great for architectural applications or for making concrete with very, very consistent coloring, okay? Then you would use white cement and maybe some other pigment to get it dead on, exactly the way you want it. This table shows the different types of ASTM C150 cement, and it shows typical average compositions done from a survey from a lot of different cement plants. This isn't from one cement plant. This is an average of a whole bunch of them. We're going to be talking about, first, the different phase compositions. Now, I've talked about these previously. C3S, C2S, C3A, C4AF, and then limestone. C3S, what's that for again? Rapid, that's for our early age strength gain. What's C2S for? Well, it's kind of an in-betweener material that we had to make to get to C3S. But it does provide some long-term strength gain. C3A produces etchenite and monosulfate. It's important for early age stiffening, okay? C4AF, not really important for much. And limestone, that's that extra material they add just to kind of, it's like extra stuff. It's laying around. It kind of tries to make it more green. So if you look at these actual compositions, we talked about type 2 cement, and the goal was to have it have a C3A content less than 8%. And look, on average, it's 6. That's pretty cool. And then here's a type 5. And on average, they want it to be less than 5%. And it's 4. It's right at the line, but that's okay. It's good. You'll also sometimes see combination cements. Like something's a 1/2, okay? A 1/2. That means it meets the specification for a type 1 and a type 2. You'll even sometimes see a 2/5. That means it meets both those, or a 1/2/5 means it meets all three. It's pretty cool when you have one product that meets so many different specifications. But to produce a type 2 or a type 5, it's usually more costly because you have to pay more attention to the ingredients that you have around you. And a type 3 is definitely more costly. Why? Because you have to grind it finer. This Blaine fineness, which we'll talk about coming up, is how fine it is. And the higher the number, this is like the surface area. The higher the number it is, it means the finer the particles. This has a lot higher surface area than any of the other cements. You'll also notice that as people started to add limestone, these Blaine numbers have gone up. That means they're having to grind their cement finer, on average, to make those limestone particles not be as reactive I'm sorry, to overcome for the not as reactive limestone particles, or because the grinding is just different with those softer limestone materials being added. These are strengths, compressive strength. This is in megapascals after 1 day, and this is in pounds per square inch. So, and we'll talk about this test coming up as well. And again, you can see the type 3's got a lot more early age strength than the other ones. And this is the heat of hydration. This is how much heat is given off during 7 days from 1 gram of cement. And again, we can see that type 3 is giving off the most heat. And look at this type 4. It's giving off the least heat. Let's move down. Now, all those strength things I was just talking about were kind of a strange test. They're mortar tests. In this case, though, this is concrete. This is all concrete made with the same aggregates, made with the same cement content and the same water to cement ratio. That's not the case with the stuff I was telling you earlier. This is a very good way to compare different cements to one another. And we can see here's type 1, and type 1 does not have the highest early age strength, but it has higher than some. Okay, and then type 1, if we follow it along here and follow it along here, it ends up right here. One trend you'll see is the higher the early age strength is, the lower the long-term strength is. But is that a problem? Is that a concern? Usually our specifications ask for strengths at like 28 days. And actually our contractors today want our strengths as fast as possible, within 3 days or 7 days, because they want to get the forms off. Or they want to move on top of that concrete to use it for something else. So early age strength has been a huge focus for modern construction techniques. And so is it that big of a deal that we don't get as long-term strength? Well, it's something to know about, but I don't think it's that big of a deal. Anyway, there's type 3, there's type 1, here's type 5, there's type 4. Type 4's got the lowest early age strength, and look up here, it's got one of the highest. The next thing that we'll be talking about is blended cements. This is Portland cement with some other stuff in there as well. So they're combined with other materials to try to get certain properties. And you could actually make these cements on your own. You could order up typical ordinary Portland cement, and you could have other additives that you could add to it, like fly ash, slag, silica fume. These are waste products from other industries. You could add them, you could blend them on site at the ready mix plant or at the batch plant. And this actually gives you a lot of flexibility. This allows you to produce concrete for lots and lots of different customers and not have to be tied to just one material. However, there are some definite advantages of having a cement producer, add all of these materials together and optimize the product for the use. And these are called performance-based cements, or ASTM C1157 cements, or in Canada, CSA A3001. And these cements are blends of OPC and other mineral admixtures, such as slag, fly ash, silica fume, limestone, all kinds of other stuff. And there's no limits to what they could use. And they don't even actually have to tell you everything that they use inside of it. But instead, they focus on performance. They focus on saying, we're going to make sure it does this, and it's going to do this really, really, really well. And they have different categories. And the different categories you're going to notice kind of follow the ASTM C150. For example, GU, that stands for what? General use. MS, that's called out as moderate sulfate. Now in the last one, we told them that they had to have a C3A content less than what? 8%. We don't do that here. This is a performance based. So it's going to perform on a certain standardized test a certain way. And that's all they need to tell you about. That's how it works. MH, moderate heat. And how would they do that? Well, it may be the chemistry of the cement. It may be the additives they add. It's not the purchaser's concern. It's kind of like, don't tell me what's in the cake. Just tell me if the cake tastes good or not, or tastes the way you want. If you want moderate heat, ask for moderate heat and they deliver it to you. The problem is that you might need general use for one project and you might need moderate heat for another project and you might need moderate sulfate for another. That can be an issue. HE, high early. So again, it's going to get you a certain amount of high early strength. LH, low heat. Really, really low heat. HS, what do you think that is? High sulfate. And again, you can read more about these actual cements, but the goal is that they're performance-based. They're going to perform a certain way on a certain test. Now, at least in Canada, they have decided to give you some insight to what they're providing by adding more information after the name. For example, they might tell you a GU, that means it's a general use, but it's B, that means it's blended, okay? Then 20F, 20% fly ash, 30S, 30% slag. Now, they don't tell you which fly ash, they don't tell you which slag, they just say this is what they use. So it gives you some insight, but not everything. And some people just like to have more control over their processes. And that's why 1157 cements have not been that popular in a lot of regions. Okay, we're moving on. Keep moving ahead. Masonry cements. ASTM C91. Masonry cements are very, very unusual because in a masonry job, you do all the mixing on site in usually small batches. And so they can't have lots of different materials. They want everything to be in the mixture that they need. Everything. They want a bagged product with all additives, all admixtures, already ready to go, that just does what they want it to do. Just add water and mix. That's what masonry cements are all about. Expansive cements. ASTM C845. These are also known as shrinkage compensating cements. And this cement, believe it or not, swells or expands from a specific reaction that happens inside the material over the first about 3 to 4 days. It actually expands and gets longer. Now it still shrinks. When it dries out, it still shrinks, just like typical Portland cement, but because it's already expanded some, once it does shrink, it will compensate for some of that overall shrinkage. This is very useful in floor slabs, for example, or any other place where shrinkage is a huge concern to you. And this can definitely reduce cracking from drying shrinkage if that is a big concern to you. And this can also be made as an additive to just add on top of a typical OPC. Now let's talk about non-Portland cements. Now, there's a whole bunch of these, all right? I'm going to talk about just a few. These are also called alternative cements. They have very different properties. They actually have lower embodied energies and lower carbon footprints. Why? Because they're not really highly calcium based. There's calcium in there, but there's a lot of other stuff in there that's important in the chemistry. So they don't have to be cooked as high, and they don't have to be calcined as much. So they don't emit as much CO2, and there's not as much energy needed to make them. And these materials are commonly used for special applications, such as if you have extreme chemical or heat resistance needs, or if you need really, really rapid strength gain, or if you're concerned about shrinkage. Let's talk about our first alternative cement. Calcium aluminate cements, also called CACs. Now this is an aluminate-based system, and it can gain strength more rapidly than OPC. It's very, very resistant to corrosive chemicals like acids and bases. If you ever need a concrete that needs to be extremely resistant to these extreme materials, extreme chemicals, then calcium aluminate cement could be the material for you. It's also extremely resistant to high heat. So believe it or not, NASA, it builds its launching pads out of calcium aluminate cements. Also, there's certain airplanes that actually take off by shooting their thrusters down on the ground. They actually make their landing pads and takeoff pads out of calcium aluminate cements because they're really resistant to heat. Unfortunately, there's some bad news about them though. The microstructure, it's not stable. It's not stable. And after 60 to 150 days, it's actually going to start to form products that are going to cause internal cracking. And your strength gain, your ultimate strength, can be reduced by 20 to 50%. That means you could be gaining strength. You could have all the strength you wanted. You tested it 28 days. You're like, man, I'm doing great. But then you get to another 28 days and you lost 20% of the strength. And you get to another 28 days and you've lost 50% of your ultimate strength. Yikes. This can be bad. If you don't understand this, this can be extremely dangerous. And this material has caused several structural failures because engineers didn't understand this strength loss. Also, when people need to make runways or structures really fast that they're concerned may be blown up in like warfare, they'll often use calcium aluminate cements. They can put them down, they get strength really fast, and they don't care if they're blown up because they're going to lose strength anyway. They're going to kind of crack themselves up and could lose 50% of that ultimate strength. Now these materials can be very impermeable, very, very good at reducing outside fluids coming in, at least until they crack. They also have a lot of something called chemical shrinkage. I mean, it's early age shrinkage that happens during the reaction. While everything is setting up and forming a structure, the material shrinks a bunch. You got to be careful for that. You got to watch out for that. So it's kind of like Portland cement, but it's bizarro, right? I mean, it loses strength. What? But it gains strength really fast. That's great. You just have to understand it. You have to design for it. The next ACM is calcium sulfo aluminate cements, CSA, or sometimes they're called calcium sulfo aluminate B-lite cements because there is some B-lite mixed in with them as well. This is another aluminate-based cement, and the early age hydration product is etronite. Yeah, those needles that grow, yeah, I know. It's almost all etronite. What? And over time, the B-lite is supposed to react and form CSH, but I'm not sure in the field if that's always the case, especially in dry environments, but that's another story. But the great thing about this stuff, this material can get strength crazy fast. I mean, crazy fast. You can get 4,000 PSI in 4 hours, and that's not hard. That's not hard at all. You can get 10,000 PSI in 1 day. 1 day! I know, amazing! There's a drawback. There's a drawback. This stuff is rapid hardening, like crazy rapid. Like it will get super hard in 20 to 30 minutes. That means if you don't get it out of the mixer, in place, consolidated, finished, in the final form, you're in deep trouble. You're in big, big trouble. Now, there are some chemicals you can add to it to try to slow it down. Those chemicals are kind of expensive though. People don't like stuff that's expensive. And they're also hard to get it just right. Hard to get it dialed in just right in the field. So a lot of times you'll see folks use this on really rapid patches where they don't necessarily need to get everything right. They dump it in a hole, strike it off, it's good. Another thing though, they'll actually use it for is they'll have on-site mixer trucks. Yeah, these are mixer trucks that carry everything to the site dry and then mixes it up there, blends and mixes it on the site and places it. Those aren't everywhere though. But if you got one, this could be a good, very, very good material for you. The microstructure is pretty strong, but it's interconnected. it means there's pores. There's not a lot of pores, but there's some that go all the way through the entire material. This means it's really easy for moisture to enter and also for it to leave. So this is good and bad. This means that it's easy for the material to dry out. And so drying shrinkage isn't a concern, okay? It's not a concern. It's not something you have to worry about. It doesn't shrink very much at all. So it's great in the desert. It's amazing in the desert. This should be the cement of the desert, ladies and gentlemen. Or any place where it doesn't rain very much. Or doesn't freeze very much. But it can perform there. It can. You just have to be careful. However, the material, at least by itself, is not that resistant to outside fluid. So using it where you're trying to protect reinforcing steel may not be a good idea. The main usage is for patches and slabs that do not contain steel or do not contain steel that we're worried about corroding. There's another one. Geopolymers are chemically activated cements, and this is a huge family, a huge umbrella. There are so many things that can fit into this, okay? But they're broad, and they have a wide range of properties. If someone says, I've got a great geopolymer, you need to realize that it's highly dependent on what they're using to make the geopolymer. For example, if they consist of materials that are mined, that come out of the ground, that are pretty pure, like zeolites, then they can actually make a pretty consistent material. This is like taking something out of the ground and activating, adding another chemical to it to make it react. But if they're using industrial byproducts like fly ashes or slags, those are more variable and harder to get right. Now, you can get them right. You can. They're just a little bit more challenging. And with all these, you need specialized activators. That means you have to tailor the chemistry of the fluid you add. This fluid basically reacts with this material and forms a cement, okay? Forms like a microstructure, a product, but you have to tailor it to what you're putting in. So it's not as equal as always using one ingredient for one other material. You have to match them up right now. At least that's where the industry is now. But once you get them right, they'll dissolve and react to form this microstructure. They can have amazing properties. And the properties and performance are highly dependent on the materials being used. But like I said before, they can have amazingly awesome or amazingly awful properties. And we need to learn a lot more about them. There's a lot of research going on around the world about them. And I think they're a potential useful tool. Thanks.